Hey everybody, sorry I'm not feeling too well and had to miss class this morning. Hopefully this recorded lecture will fill in and get us ready for the final. And if you have questions about the test, please email me and I'll try and get back to you as quick as I can. I'll be watching my email through the day. Thanks for any of you who have been praying for me. I am feeling somewhat better as the day wears on. Let's jump in here. Right here, this we've seen last time we talked. That's Planck's constant. That equation comes in where we talk about the energy of a photon. We talked last time about the photon theory of light. We said that the energy of a photon was Planck's constant times the frequency. And frequency, if you remember, frequency is the inverse of the period. And the period is the time for one cycle. Talking about repetitive motion. Waves have repetitive motion. There's a peak and a trough, and how long does it take for one cycle to occur? Circular motion is repetitive motion. How long does it take to go in one cycle? And there's another number here that we introduced last time, lambda. This is the wavelength, and it's exactly what it sounds like. It's the distance from peak to peak of, say, a water wave going across a lake. If you were to measure with a ruler the distance from the peak of one wave to the peak of the next wave, the crest of one to the crest of another, that would be the wavelength. And there's a relationship that we want to make use of. This is true for all waves, sound waves, water waves, light waves. It doesn't matter the kind of wave. There is a relationship that says frequency times wavelength is equal to the velocity of the wave, where v equals the velocity of the wave. And for light, we know the velocity wave. V equals c. For light, the velocity of the wave is c, 3 times 10 to the 8 meters per second. For all other kinds of waves, water waves, sound waves, you have a velocity, you have the speed of sound in air, and you have the speed of a water wave traveling across the pond or on the ocean. Waves travel at a certain speed. The crest of the wave rolls forward at a certain speed. That's the velocity of the wave. But for light, we know this. This is something, because of Einstein's special relativity, everybody measures light with this speed c. So this is a velocity that is well known, well understood. And so for light, our equation becomes the frequency of light times the wavelength of light equals c. So these are equations. This is for any wave, and this is for light waves. Talked about the fact that light is a wave. And we're going to make use of that. We'll see that equation become handy. Sometimes the homeworks are going to talk about wavelength, sometimes they're going to talk about frequency, and here's the connection between wavelength and frequency. You can use this equation to connect from wavelength to frequency, or if someone gives you a frequency of light, you can calculate the wavelength of the light by using this equation, just doing the algebra. Okay, then there are a couple other things I wanted to make sure I mentioned here. Here's a conversion that we're going to be using for energy. We're going to talk a lot about energy in this part of the course. We've talked about joules, but there's another kind of energy which is more commonly used when we're talking about atoms and energy transitions in atoms, and it's called the electron volt. It's in the front cover of your book, so I'm just putting it here just to highlight it, but it is in the front cover of your book. 1 electron volt is 1.602 times 10 to the minus 19 joules. And we'll be making use of this because many times homework problems will give you energies in units of electron volts, or I'll ask you for an energy in electron volts in Math Excel, but the equations that we use are often going to need you to work with energy in units of joules. So you're going to have to be able to convert back and forth between electron volts and joules. And again, you have to look at the units involved in the equation, and if there are energies of photons, that's Planck's constant is involved in the calculation of the energy of a photon, and that constant, Planck's constant, has joules in it. So that means when you use that equation, when we use this equation, the energy of a photon, we better have the energy of the photon in joules, because Planck's constant has joules in it. You don't want to have a units mismatch. So again, you got to be paying attention to the units before you start crunching the numbers. Make sure the units are consistent throughout the equation. Convert the numbers so that the units are consistent, so you don't have inconsistencies in the units. And we're going to be introducing today in the lecture something called the Rydberg constant. And this is that value, 1.097 times 10 to the 7. And the units are a little strange, 1 over meters. This is not a mistake. It's not some funny new kind of unit. This is 1 over meters, inverse meters. That's the units of the Rydberg constant. And we're going to talk about atoms and how atoms and electrons in atoms do what they do and produce light by what they do. And we'll talk about the hydrogen atom. So let's first revisit the photoelectric effect, because we didn't really do any calculations with that, and I wanted to make sure we did a couple of calculations to show you how that kind of calculation goes. So let's just review where we were. For the photoelectric effect, you remember that we had light shining on a piece of metal, and then electrons would come off. And the equation that was governing the photoelectric effect, or that described accurately the photoelectric effect, was the energy of the photon that hit the metal could go into two places. Could go into the work function and could go into the kinetic energy of the electrons. And as we enter into this part of the course, it's going to be important for us to have a couple more constants that we're aware of, that we're going to make use of often. One of those constants, and we had it on the board the other day, I just want to reiterate it here. The mass of an electron, all electrons have the same mass, 9.11 times 10 to the minus 31 kilograms. That's the mass of an electron. The charge of an electron, as you know, is minus 1.602, so this is the Q of an electron is minus 1.602 times 10 to the minus 19 coulombs. And if you look in, we're in chapter 39 and 38 of your book, the last two chapters of your book. If you look in the beginning of chapter 39, you'll see a table that has the mass of an electron, the mass of a proton, and the mass of a neutron. And those are numbers that we're going to be using pretty consistently. So when you find that there's a problem that deals with protons or electrons or neutrons and you need the mass, look it up in that chart in chapter 39. And that way we're all using the same numbers. If you look it up online, you might get some slightly different numbers, which could cause you some trouble with Math Excel. So I'm using the numbers that are from chapter 39 in the book. So that's where I want you to go to find that information. Okay, why is that important? Well, because the kinetic energy in this equation refers to the kinetic energy of the electrons that come off of the metal. So the equation is going to have the mass of an electron in it. The kinetic energy of the electron is 1/2 mass of the electron times the velocity of the electron squared. W is the work function. That's how much energy the atoms in a metal hold on to their electrons. So my my photon has to have enough energy to overcome the work function and pull an electron away from the metal. Okay, and E photon obviously is photon energy. So let's just set up a problem here and show you how this works with some numbers. Let's say, for instance, that we have a photon. Let's see, let me give you this. Let's say this. The work function for a particular metal is 3.5 electron volts. That's the work function for a particular metal. And let's say that I have an experiment where I need to have the kinetic energy of the electrons that come off the metal. I need that to be 7.5 EVs. And so the question is, what frequency of light do I need? What frequency of light do I need? What frequency of the photon do I need in order to create these electrons with this much kinetic energy? Okay, so I have energy of a photon, a certain amount of energy. It has to provide at least 3.5 electron volts of energy in order to pull an electron away from the metal. And then it needs to have an additional 7.5 electron volts in order to give the electrons the kinetic energy that I want. So clearly from this equation, we can say the energy of the photon is the 3.5 EVs plus the 7.5 EVs, which is going to be 11 EVs. So I need a photon with 11 electron volts of energy. And the question is, what's the frequency of such an such a photon? Well, we have to use our other equation. Our other equation says that the energy of a photon is Planck's constant times the frequency. So the frequency, if I do the algebra, then I'm going to get the frequency is the energy of the photon divided by Planck's constant. And now we need to make sure we're careful because, as we discussed a moment ago, Planck's constant has energy units of joules, and we're now working with energy units of the photon in EVs. We have an energy unit mismatch. So we have to convert this 11 EVs into joules in order for there to be the ability to use this equation and get a correct number out. Okay, so let's convert the 11 EVs. So we're going to take 11 EVs and we're going to convert to joules. So we take the 11 EVs times a fraction. And I want joules in the numerator and I want EVs in the denominator. And at the beginning of the lecture, I told you that 1 EV was 1.602 times 10 to the minus 19 joules. So I have to do this calculation, right? And so we're going to say 1.602 exponential 19, change sign, here we go, exponential minus 19 times 11. And this is one thing I don't like about this calculator built into Windows. I got to count all these places now. So let's see, 11 is going to be 17.62 times 10 to the minus 19 joules. Okay, so that's what we're going to have. And now we can do our calculation. So I can now say frequency is 17.62 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34 joules per hertz, and this is joules up here. See, the joules are going to cancel. I'm going to get hertz as my result. So I get 17.62 exponential 19, change sign, and divided by 6.63 e 34, change that to a negative, and I get 2.66 times 10 to the 20 14, 15 to the 15 hertz. Yep, 2.66 times 10 to the 15 hertz. So there is the frequency of the photon that I would need to have in order to generate the problem where I have a work function, I have a metal that's holding on to its electrons with this much energy, and then I want the electrons to have this much energy when they come off the metal. I would need to have photons with this frequency, 2.66 times 10 to the 15 hertz. And there are, all kinds of variations on the theme that you can use. But these are the equations you're going to be using. You're going to have to make use of several of these different things. Now, here you're going to have to definitely make use of the energy of a photon calculation. You're going to have to make use of the conversion from EVs to joules. That's often going to be the case. You may have to use this equation if I give you details about the electrons and I want to know the velocity, or I give you the velocity and I want to know the kinetic energy. Okay? But again, this is the fundamental equation that you're going to use when we talk about the photoelectric effect. Always start with that and then see what else you need to use in order to fill in the blanks. But this is the fundamental one you should always go to when I'm telling you that we're working on photoelectric effect. Okay, so there's at least one example of a photoelectric effect kind of calculation that you're going to find in the homework and ultimately on the final exam. Now what we want to talk about is the idea of momentum. And momentum is an important idea. You remember that was the idea we started talking about when we derived the E equals mc squared equation. And momentum is a big deal in physics. And it turns out that we know that momentum for a particle is mass times velocity. We've done that since the first part of the course. The momentum of some object is its mass times its velocity. Then when we did the relativity stuff, we found out that the momentum of a particle, P momentum for a particle, relativity included, is gamma times m times v. That was one of the things we stumbled across as we were working on the E equals mc squared equation. deriving that. This is the result that we got, that relativistic momentum has this gamma in front of it. And remember, gamma is 1 over the square root of 1 minus beta squared, where beta is the velocity, the dimensionless velocity of the moving observer. But we are also going to have now a result of quantum physics is that we also have the momentum of photons. Little bundles of light have momentum. It's a strange result. This only came to be understood in the 20th century. It's part of modern physics. Previously, momentum was thought to only be applied to particles because we had mass involved. And light, as we talked about the other day, has no mass. So the thought was, well, there's no momentum in light. But that's not true. It turns out that light does have momentum. And there are experiments that have shown this. One is called the Compton effect, where I actually collide a photon with an electron. And I can conserve momentum. I can see the conservation of momentum when I collide a photon with an electron. And it turns out that the momentum of a photon is Planck's constant divided by the wavelength of the photon. And let's just check and make sure that this has the right units, okay? Let's just check and make sure that this has the right units. So we're going to do dimensions. So we're going to do a dimensional analysis of this. So H has the units of joules per hertz. Those are the units of H. And wavelength has units of meters. Okay? So I can rewrite this not as a complex fraction, but as a regular fraction. I can go joules over, put the hertz down in the denominator here. Okay? And now a hertz is 1 cycle per second. So I can rewrite this. Again, I'm just doing algebra on this. I have a joule over 1 over seconds. Remember, frequency is 1 over the period, and period has units of seconds. So it's 1 over seconds times meters. Well, this is a joule times a second. Now that second that's in the denominator of a fraction that's in the denominator gets to go to the numerator, comes up to the top, over a meter. So now we've just simplified this again. A joule second per meter. And remember, a joule is a Newton meter. So a Newton meter times a second over a meter. Okay, so then we're going to get these meters to cancel. So I have a Newton second. So I'm going to do this again, a Newton times a second. And then a Newton is a kilogram meter per second squared. That's a Newton times a second. And if I do that, I'm going to get a kilogram meter per second. And those are indeed the units of momentum. Because momentum is mass times velocity, and these have the right units. So h over wavelength has the same units as momentum, and yet we're talking about a photon here, and a photon has no mass. But here we have an equation that comes out of quantum mechanics, quantum physics, that has no mass required. I just have Planck's constant and the wavelength of a photon. So here is an important equation for us that we're going to use. And now we know that a photon has momentum. So when it collides with something, the collision, remember, momentum is an idea that we have when things collide. When a photon collides with, say, an electron, it will give some of its momentum to the electron. And this equation says that when a photon gives away some of its momentum so that it has less momentum, that's going to change its wavelength. And if you change its wavelength, we know that you're going to change the color of the photon. And that actually is what happens. The Compton effect shows that the color of photons change after a collision, and there is also momentum imparted to the electron, and we can measure how much momentum has been imparted to the electron due to the collision. And it all works out that when we have this much momentum associated with a photon, the experimental results make perfect sense in terms of conservation of momentum. So this is another area where we have this wave particle duality. We have light, which is a wave, but now we have it with a particle-like property, momentum. So sometimes we talk about, in quantum physics, sometimes we talk about the wave nature of light, sometimes we talk about the particle nature of light. The wavelength is a wave property, the momentum is a particle-like property. Okay, now it's going to get even stranger. Let's add a little bit of strangeness here. The momentum of a particle is also h over lambda. The momentum of a particle is also h over lambda. This is another one of the strange results of quantum physics. And we also know that it's the mass times the velocity. So we have two equations for the momentum of a particle. One is mass times velocity, which is the classical view of momentum, and one is h over lambda. But particles don't have a lambda. Particles are not waves. We're not saying that when an electron flies through space, it goes up and down and has a wavelength. That's not what we're saying at all. Instead, here's the strangeness of modern physics. The wavelength of a particle describes a probability distribution curve. In modern physics, particles traveling with a momentum have what's called a probability distribution associated with that motion. So one of the ideas of modern physics is that real particles with mass have some kind of probability distribution. And what I mean by a probability distribution is this. If I have a function the probability that a particle is located at any particular location, this is the x-axis, this is the position location. Where is a particle? Well, a particle is most likely to be where its probability distribution function has a tall or a high amplitude. But where it has a small amplitude, like out here in these tails, the particle can still be there. It's just there with less probability. So in modern physics, we can't exactly say where particles are located. We can say they're located most probably here, but there's a probability that it could be here or it could be here. So we have this uncertainty in the position of a particle, and that uncertainty is part of modern physics. We have to start talking in terms of statistics and probability distributions. So some of these functions can look kind of like this. Where if I make there's a wave inside a wave here. Look at this. Here I have a wave, and if I connect the peaks of the wave, I get something that looks like the thing I drew above. This thing has a wavelength. The distance from peak to peak is the wavelength of this wave. That's the lambda that we're talking about. Particles have some kind of a wave associated with them, and it's the distance from peak to peak. But it's not saying that the particle travels in a wave that goes like this. It's saying that it's most likely that the particle is here where the amplitude is high, and it's less likely to be out here where the amplitude is low. But there is still a probability that I could have a particle out here in the tails of this distribution function. Okay, so here's the upshot of all of this. The important things to remember. Particles now have two equations for momentum. Our classical result, mass times velocity, and our new quantum result, Planck's constant divided by the wavelength of the particle. And this wavelength is not a physical wave, it's a statistical wave. This is an equation for the momentum of light photons, h over lambda. This lambda is now the real wavelength of the light particle, of the photon. The photon is defined by having a wavelength. So this wavelength is our traditional understanding of a wavelength. And as I mentioned the other day, light has electric fields that oscillate up and down and get big and small. And if you connect the tips of those electric fields, it looks like a wave, looks like a sine wave. And the distance between peaks is the wavelength. And so you got to now be careful when we're doing problems. You have to be very careful about whether we're talking about electrons or protons or photons. Photons are light, protons are particles, electrons are particles, neutrons are particles. And just make sure you're keeping straight which kind of thing we're talking about. If it's a photon, you got to use this equation for momentum. If it's a particle, you've got two choices. Depends on what the question is as to which one of these you're going to use. All right. So let's see how this gets used. And let's do we're going to now talk about the Bohr hydrogen atom. There's a guy, a Swedish guy, a Danish guy named Niels Bohr, who described the hydrogen atom and some of the details of how it worked. And, you know, if you look up at the fluorescent lights in our classrooms at the school, those fluorescent lights are filled with gas, and we put electricity on that gas, and the gas glows, and we get white light coming out. A few more steps involved, but basically that's what happens. I put electricity or energy into a gas, and I can make it glow. You see this on neon signs. You can put electrical energy into a tube that contains neon gas, and it'll glow red or blue or green, depending on the exact composition of the gas. And Bohr was trying to explain what's called the light emission spectra of hydrogen. If you look at the light that comes off of hot hydrogen gas, like a star, stars are made of burning hydrogen for the most part. And if you look at the light coming off of hot hydrogen gas, it has a fingerprint. There are only certain frequencies of light that come off of hot hydrogen gas. And there's a lot of frequencies there's no light coming out at a lot of frequencies, at most frequencies. There's only a few specific frequencies that light comes out of hydrogen gas when it's heated up or when it's energized. And Bohr was trying to explain how this could occur and what was going on. And so the center of a hydrogen atom is a proton, which is a positive charge. And then we have an electron outside, and it circles around. And there's some radius of the orbit. So this is an orbiting electron. And that electron has a velocity, which means it has a momentum. So here comes the idea of momentum. And this atom this is very much like the moon and the Earth. The moon circles around the Earth. Why? Because there's a force of attraction called gravity between the Earth and the moon. Well, there's a force of attraction between an electron, which is a negative charge, and a proton, which is a positive charge. But because this electron is moving, it never falls in and hits the proton. It just circles around. Okay? The motion tries to take it away from the proton, but the attraction keeps pulling it back, and the combination of those two forces, those two things, makes for circular motion. And this is our old friend circular motion. We've talked about circular motion before. Just to remind you, circular motion is F centripetal equals mv squared over r. Remember that from way back when. So Bohr took this idea of classical physics right here and said that the centripetal force is the force of attraction between the proton and the electron. And that's our old friend. Electric force is K electric QC QF over R squared. That's Coulomb's law. So he took that. That's the centripetal force. The mass is the mass of an electron. The radius is some radius that the electron has around here. And what he did is he added an additional feature. And the feature was this idea that the electron has a wavelength. So let me try and draw in here a wavelength for this electron. And this is going to be a little funny. Let me see if I can make this wave on here. Okay, so there's a wave, very, very bad wave. But usually we draw a wave, usually when we draw a wave, it looks like this. And usually there's some dotted line straight through the middle. Well, what we've done is we've taken the dotted line and we've made this circle out of it. Okay, this circle here is that dotted line. And then I've tried to draw the humps above and below to have the wavelength represented here in some way. It's not a great drawing, but I hope you get the idea. And here's the idea. In physics, there's a pretty fundamental idea. Waves interfere with each other. When two waves cross each other, they don't collide and bump and bang. They just kind of pass through each other. When two light waves hit each other, they just pass through each other. There's not the typical collision like we have with particles. Light passes through waves, water waves. When they meet each other, they don't collide and bump off each other. They just pass through each other. But when a peak of one wave meets a peak of another wave, we get a big peak. And when a trough of one wave meets the trough of another wave, we get a big trough. And when the peak of one wave meets the trough of another, we get nothing. They cancel. These are known as constructive interference. And this is known as destructive interference. So here's how Bohr used this idea. This is a very well-known idea from water waves and sound waves. If anybody's done acoustics, you know there are dead spots, like if you're doing the speaker system design in your church. If you put the speakers in the wrong places, you're going to get dead zones where nobody can hear anything, right? The sound just kind of disappears. And it's because there's this interference in the waves, and you can get dead zones where peaks and troughs meet and they cancel and you get no noise, no sound. So Bohr said this: if we have a wave associated with the electron, right? So here's the electron, and now we're saying there's a wave associated with it. If the wave, which is going around in a circle, so it kind of overlaps itself. Every time it goes around, it overlaps itself. If the wave meets, like I've shown here, where the wave, the end of the wave meets the beginning of the wave, and they just kind of fall on top of each other, then each time the wave goes around, it's going to constructively interfere. And the wave is going to constructively build itself. Whereas if the wave traveling around the orbit doesn't match exactly where you start and where you end, if they don't match exactly, you're going to get destructive interference. And you're going to get peaks and troughs meeting, and you're going to have the wave being diminished in size. And what Bohr said was, well, if these probability waves are such, if I have a big probability wave, then that means that's where the electron is going to be. If I have a small probability wave, that's going to say where the electron is not going to be, or is less likely to be. And so what Bohr did was he solved all the equations and found the particular orbits. There are only certain orbits, certain radius orbits, where the electron wave meets itself when it goes all the way around the orbit. Where it begins and where it ends, they match and they meet each other. And then I get constructive interference between the wave and itself. As it comes back around on top of itself, it builds and it builds and it builds, and that says the electrons can be in that orbit. Most other radius orbits can't have any electrons because the wave associated with the electron gets diminished and diminished by destructive interference. So here's the picture that Bohr came up with. I have a proton and I have electron orbits. The allowed electron orbits, there's only certain ones. The electrons can only be in certain orbits around the proton. And we number these orbits 1, 2, 3. 1 being closest to the proton, 2 being the next out, 3 being the next one out. And everywhere in between is a dead zone. No orbits are allowed. No electrons can exist in any orbit between these two or between these two. That's dead zone. And this is where the idea of a quantum leap comes from. Electrons can only exist here or here, and they can never exist in between. They must make a quantum leap. If they're going to change from one orbit to another, they must make a quantum leap from one to the other. Okay? Must make a quantum leap from here to here. Okay. So here we have this idea of orbits, numbered orbits that are very, very precise. Only these orbits can exist in the hydrogen atom. Here's the other idea that we should know by now, is that the laziness principle says that particles want to be wherever there's the lowest potential energy. And since these electrons are being attracted towards this proton, the orbits closer in have lower potential energy. Then this has higher energy, This has higher energy. The further you get away from the proton in the center, the more the energy, the higher the energy. Well, electrons don't want to be where there's high energy. They want to be down where there's low energy. They'd like to be in closer. They'd like to be in this orbit, down in here. Okay? So here's the theory. Here's Bohr's view of the way this works. If I, in fact, have an electron out here in orbit 3, it wants to be closer. Let's say it jumps all the way down to orbit 1. So it goes from 3 to 1. It used to have a lot of energy out here. It used to have high energy out here in this orbit, and it's going to have lower energy here in this orbit. When it makes the jump, it has to get rid of some energy. And so what Bohr said was, it throws away a photon. And the photon carries away the extra energy that the electron no longer needs because it's going to a new orbit, and that new orbit has a lower energy. So a photon carries away the excess energy. This is where the light comes from when you heat up hydrogen gas. Heating it up means that you can make electrons jump out here to higher orbits than they would normally like to be in. Because you're putting energy in, they can jump out here to a high energy orbit. But then eventually they're going to want to jump back down to low energy orbits. And when they do, they're going to throw away a photon. And that's the light that we see. And when Bohr did this, he came up with an equation that looked like this. Here's that Rydberg constant. And now we can see why the units are 1 over meters. The units of the Rydberg constant are 1 over meters because this side of the equation has to have the same units as this side. Well, this side is 1 over meters because wavelength is meters. So the Rydberg constant, 1.097 times 10 to the 7, inverse meters. These are just integers. These are the ends that are the orbits. The orbits are just 1, 2, 3, 4, 5, 6, 7. And if I plug into this equation, the orbit, the low orbit and the high orbit, this calculation, this equation will calculate the wavelength of the photons that come off of the hydrogen gas. And it turns out that this formula is exactly the same as a formula that was known from experiment for many years. No one knew why it worked, but people knew that this was the right equation that described the hydrogen spectra. It wasn't until Bohr came along with his theory that we could understand why this formula works. He could explain exactly what was going on inside the hydrogen atom to make the photons that describe hydrogen. The particular fingerprint of hydrogen is described by this equation, and he then was able to give theoretical justification for what had prior to that been only an experimental result. Physicists had looked at the results of experiments for years and had just come up with this equation by hook and by crook, by careful mathematical manipulation, but they didn't know the theory of why that equation worked. Not until Bohr came along and included this idea of the wave associated with a particle, the wave associated with the momentum of a particle. Then there was a reason for this formula to work. And everything other than that was just classical physics. These are equations from classical physics. So Bohr was able to describe this. So let's see how this works out. Let's do a quick example and then we'll finish up. Let's say we have a hydrogen atom electron starts in orbit 3, jumps to orbit 1. What is the lambda of the photon that's created? All right, so we're just going to make a direct application. It's the problem we've been talking about here, the example I've been talking about. So we're just going to plug the numbers in here. So we're going to have 1.097 times 10 to the 7 inverse meters times 1 over 1 squared, because that's n low is 1, minus 1 over 3 squared. Okay, so it's 1 minus 1/9. Okay, so we're going to have 8/9 times, so we got 8 divided by 9 times 1.097 E7 9.75 times 10 to the, what do we got here? 3, 6 times 10 to the 6. Okay? 9.75 times 10 to the 6. Now remember, this is 1 over lambda. This is 1 over meters. So this is 1 over lambda. So lambda is the inverse of this. So there should be an inverse. Let's see, do I have an inverse in here? Where's my inverse button? Tangent, cosine, degrees. 10 to the x squared. Let me see what I got here. Here it is, 1 over x. Okay, and I've got 1.03 times 10 to the minus 7. 1.03 times 10 to the minus 7 meters. Okay, 1.025, so I rounded up 1.03. All right, so that's the wavelength of the photon. This is the photon wavelength. And then if I said, what's that frequency? Oh, okay. So here's where we have to use our wave equation, where we said frequency times wavelength is c. So we can say, do the algebra. The frequency equals c over wavelength. This is 3 times 10 to the 8 meters per second divided by 1.03 times 10 to the minus 7 meters. Okay, and so this is going to be, I'm going to take 1 over this again, and then times 3 E8. Frequency equals 2.93 times 10 to the 15 hertz. Okay, if I counted all that up, it'd be 10 to the 15. All right? 2.93 times 10 to the 15 hertz. What's the energy of that photon? It's Planck's constant times F. All right, so now I've got the frequency. I'm going to multiply by Planck's constant times 6.63 E34 negative is 1.94 times 10 to the 19, 10 to the 19, 10 to the minus 19 joules. Okay, because remember, the units in, the energy units in Planck's constant are joules, so this is going to come out in joules. 1.94, right, times 10 to the minus 19. And how is that in EVs? Convert to EVs. I've got 1.94 times 10 to the minus 19 joules times a fraction, and I've got 1 EV is 1.602 times 10 to the minus 19 joules, so I got to divide by 1.602, divide by 1.602, EE 19, change sign, 12.11. 12.11 EVs. Okay, so there's, we're just multiplying and dividing, some straightforward things. None of the equations is terribly difficult. Okay, but you just got to realize how these things are all related. Okay, that's enough for today. Thanks for everybody. Hope this is helpful.